Welcome to Lecture 27B, and this is an extension to 27A, where we're basically going to apply the divergence theorem, but to a very specific problem in which superposition must be invoked. So the material for this lecture comes from reading assignment 5. You may want to look at section 2.4, section 3.2, since we're going to be dealing with cylindrical geometry, section 3.5, and additional problems in section 5. Also, you may want to make quick reference to reading assignment 0, section 5.2, and also lecture 1, part A. So the objectives are, we're going to apply superposition and the divergence theorem for an electrostatics problem, and the concepts, visualization skills are more or less to illustrate the procedure for determining the total field using superposition for an irrotational example. As usual, the second slide is more or less a summary of the slides to follow. So we'll just move on. Okay, so this slide is to sort of give you some sort of idea as to the different symmetries that we're dealing with. And so the symmetries when we're dealing with irrotational problems are spherical symmetry, cylindrical symmetry, and planar symmetry. And you'll notice here, for instance, if it's spherical symmetry, then there's a point of symmetry. If we're dealing with a cylindrical symmetry, there's an axis of symmetry. And if we're dealing with an infinite plane, and there's planar symmetry. In other words, there's a plane that bisects this slab. And so this would basically be the plane of symmetry that we're dealing with. You can play with this interactively to move these things around to see how these different vectors will change. Slider P is basically moving the cylinder, slider Q is moving the sphere, and slider R moves the plane. So the black arrows basically from the origin to the observation point. This is the observation point. The red arrows, which are this one and this one, from the origin to the axis symmetry and from the axis symmetry to the observation point. So you'll notice these are more or less perpendicular to the axis of symmetry. And since it's cylindrical coordinates, basically it's the distance is r, which is in a plane which is parallel to the xy plane. For yellow, from origin to point of symmetry and from point of symmetry to the observation point. And so the point of symmetry would be the origin to this point and from here to the point of observation. So in an actual fact, when we solve this particular problem, we'd like to have this point sort of aligned with the origin because we know how to calculate that problem. And then we can translate things back knowing what the relative position was with respect to the observation point. And so that's why you see two arrows here, that's why you see two arrows here, and that's why you see two blue arrows here, where the blue arrows are from the origin to the plane of symmetry and from the plane of symmetry to the observation point. So these are three cases we'll look at. In our example, we're just going to look at example where we have two displaced cylinders. All right, just a quick review of the symmetry and the computational steps. I mean, we discussed this already in the last lecture, so I'm just repeating myself here. So if you have a field F1 due to a row 1 and you have a field F2 due to row 2, and if you sum the two fields due to the contribution of row 1 and row 2, essentially, basically, it can be done. All right, so this is just basically stating the principle of superposition. All right, so how we're going to calculate the total field, where now basically we could have charges, distributions of different geometries at different locations, and so we need to know how we're going to do a calculation. So these are more or less the four steps. We compute the field for each object, assuming objects are all centered at the origin for spheres, aligned with the axis symmetry for cylinders, or lie along the plane of symmetry, which is aligned with one of the principal planes. It's, of course, we're dealing with infinite planes. So if it's parallel to the xy plane, then basically the plane of symmetry would be the xy plane, and you'd be bisecting the object. The next step would be to convert each field into Cartesian coordinates. So you solve each one of these problems independently, and then you transform them into Cartesian coordinates. The next thing to do is to transform the fields to represent the physical location of the original objects with respect to a reference point, usually taken to be the origin, but not necessarily the case, and compute the field for each object at the observation point. Once you've done that, Then you basically have a common reference point, so you can sum the fields to obtain the total field F, which will be in Cartesian coordinates. All right, and so just two specific notes here. Recall that the principal supervision states that the total field at a point is a sum of all the individual fields at that point, focusing on the field produced by each geometry individually and then adding up all the field contributions. Second note is that not all problems will require converting the geometry into Cartesian coordinates. Depending on the geometry, you may choose which coordinate system will result in the simplest calculations and appropriate symmetry, but this comes with practice. All right, so here's the example we're going to work with, again using the divergence theorem. And so there are two pictures here, one here which is a perspective diagram, and this is an XY trace. That's basically a cross-section taken so that you're looking at the XY plane, looking downwards. So you'll see here we have an infinitely long cylinder intersecting with another infinitely long cylinder, and the red cylinder has a uniform charge density of minus rho naught, and the blue has a uniform charge density of rho naught. And the observation point is located on the x-axis at this point. And so what we're wanting to do is to compute the field at this location due to these two objects. But typically I wouldn't draw this picture. I would essentially give it to you in the form of a table, such as shown here. So you'd be given a charge density distribution, rho of 1, given as follows. So if you'll notice here, each one of these describes a region. So this basically would say that it's outside both cylinders. So for instance, if I say 0 for x squared plus y minus 0.5 greater 1, and, so logic and x plus y plus 0.5 greater than 0, that would represent basically everything that's outside both cylinders, out in this region. I also have that another condition, it would be 0 inside both cylinders. So this purpley area that you see, this is the intersection set. I would say that that's 0 on the inside. So you'd have a charge density in a sort of a three-quarter moon, and you have a different charge density in this three-quarter moon, and 0 in the middle. That's more or less how the problem would be stated. I've just basically drawn a picture which represents exactly the same thing. And so this represents the conditions where you're inside both cylinders. All right, so then we have basically another condition, rho naught. So the rho naught would be the blue cylinder excluding the overlap region, would be just in this section. And then the red cylinder excluding the overlap region, which is described by this region, which is just this region here, which is in this sort of three-quarter moon section. And so given this information, not the picture you have to draw for yourself, compute the total field at the observation point here. Okay, so this basically describes this, but you could look at this as being one cylinder and a second cylinder and treat each cylinder as an individual problem. But the first thing you would do is take this cylinder, move it back so that its axis of symmetry is aligned with the z-axis, and similarly you do the same thing with the blue cylinder. And then basically you're ready to solve the problem. And this is just the trace basically to show you the region where there's a charge density, this region there's no charge density, this region there's opposite charge density, and the exterior region there's also no charge density. So just again a summary, pictorial description of the geometry is given to you on your left. Summing the charge distribution for the blue and red regions, you obtain a value of 0 in the region where the two cylinders intersect. And you treat the blue and red cylinders as independent objects. So you end up with two sub-problems. So you have to compute the field for two separate cylinders. All right, so this is just a summary of things that we already know, but I like to sort of remind people these are things we're going to have to do. These are the general principles when applying the divergence theorem to solve irrotational problems with a high degree of symmetry. And so this is the left-hand side of the divergence theorem. This is the right-hand side. But because of the specific physical problem we're dealing with, divergence of f is equal to rho, and rho is a given. And so this part of the problem is a given. All right, so again, just a reminder, the differential area vector convention, the differential area vector NSDS points outwards from the Gaussian surface enclosing the volume. We're dealing with cylinders here in both cases. So how many discrete surfaces basically create a closed surface? 3, because you have a bottom and a top surface to the cylinder and the exterior cylindrical surface. Second, we're going to choose the Gaussian surface so that on any segment of the closed surface, one of the following 3 conditions is satisfied. Either f is perpendicular to the differential surface area vector on that surface, or f is equal 0 on that surface, or f is parallel to NSDS, and f dot ns is uniform along the Gaussian surface. So we want to exploit any one of these three, in which case the problem is solvable. Third, the right-hand side of the divergence theorem needs to be broken up into piecewise continuous regions if rho is not continuous. In our case, basically, you have rho existing within the circular object, and then it's not equal to 0 outside, which means that each cylinder, you have to describe it in terms of two regions, inside and outside the cylinder. Fourth, for any given geometry, the left-hand side of the divergence theorem needs to compute it only once and can be committed to memory, but you should state what you're doing without going into details. And fifth, in the event that two or more objects have a similar symmetry, example, nested cylinders or spheres, share the same axis symmetry or symmetry point, then there's the option to solve the problem as a single problem without resorting to superposition. You can use superposition, but it's just basically another level of, another layer of work. Okay, so now we basically work through our procedure for computing the total field. So we're going to solve the field for the cylinders with respect to a common axis of symmetry. So we're doing that for both the blue cylinder and the red cylinder. And so we're applying the divergence theorem. All right, since we've already solved the case of cylindrical symmetry, I'm not going to redo it. It's left to you as an exercise to do the computations along the line spelled out in section 3.2 of reading assignment 4, or to review lecture 26 for the calculation procedure. The final results are here. This is basically in cylindrical coordinates for r greater than or equal to 1. It's basically going to be inversely proportional to the radius, and for r less than 1, it's proportional to the radius. So this is for the blue cylinder, and this would be for the red cylinder. Don't forget, in one case the charge density was positive, in the other case it was negative. So this is where both cylinders basically have an axis symmetry that's aligned with the z-axis. And now we have to basically move those two cylinders to their rightful place so that we actually capture the correct, the problem that we started with in the first place. Okay, so here I've just repeated what it looks like in cylindrical coordinates. The next step basically is to convert into Cartesian coordinates. So we know that the r hat vector basically is a unit vector, has this form, and we know that r is basically the square root of x squared plus y squared. So you can see it showing up here. In this part here, it's proportional to r, and so you can see it's the square root of x squared plus y squared. So this is for the blue case, and for the red case, which only differs by the factor of minus for the charge density, we now basically have transferred everything into Cartesian coordinates. And the next step would be to translate this information back to the original coordinate system. All right, so field translated with respect to the reference axis. And so, for instance, we would look like, for instance, outside the cylinder. If we're looking at the blue cylinder, outside the cylinder, this is what we would expect to see. If we were outside the red cylinder, this is what we would expect to see. If we're inside the blue cylinder, we would expect to see this. And if we're inside the red cylinder, we'd expect to see this. But then we'd have to look at the various combinations depending on our location. So if we're inside both cylinders, then these are the two fields that apply. If we're outside both cylinders, then these are the two fields that apply. If we're inside one cylinder and outside the other cylinder, then we could either have this combination and this combination, or this combination and this combination. So there are four possibilities to consider, but depending on where the observation point is, will to tell you which combination basically applies. Right? And so this is basically determined by just a vector translation. And so these are the results we're going to be working with. All right, we're going to compute now the field of the observation point. We set it up such that it's an arbitrary point. And so now what we can do is basically decide what x is, y, and z. The observation point was 4, 0, 0, which means x equals 4, y equals 0, and z equals 0. And so we make these substitutions into both of the expressions. By the way, since the point 4, 0, 0 is outside both cylinders, then both of these conditions are external to both cylinders, and so these are the two field field values that we'll be using in computing the total field. So we just substitute x4, y equals 0, and z equals 0 into these two expressions. If we do that for the case of the blue cylinder, then the field for the blue cylinder will just be 32.5 rho, 4x hat minus 0.5 y hat. If we do it for the red cylinder, then we end up with minus 32.5 rho hat, 4x hat plus 0.5 y hat. The last step is to compute the total field. So we just add these two together, and we end up with minus 32.5 rho hat y hat. So this basically would be the final answer at a particular observation point. If we were to change the observation point, then two things would apply. One is basically find the combination that you should be working with. And then having done that, then you would substitute the specific values of the observation point into the two expressions that you determined. Once that's completed, then the last step is to sum the results. So that concludes Lecture 27B. Thank you for listening.